In this lecture, we're going to finish Chapter 4. We have Section 4.4, which is about limits from the left and right and types of discontinuities. We're going to start Chapter 5, which is differentiability. So, let's talk about limits from the left and right. So previously we talked about limits, and limits were defined in terms of arbitrary functions between metric spaces, and now we're going to focus our attention just on functions defined from subsets of the real line into the real line. So let's assume that f is defined on some interval pq, where q is bigger than p. So here what we're doing is we're assuming our function is defined at p and at least for a little bit to the right of p, but not necessarily to the left of it. Okay? So we say the limit as x approaches p from the right, so this plus superscript on p means x is p plus a little bit, which means x is to the right of p. F of x equals L if, and here we see a very similar definition to the usual limit without the plus here. So we want to think about, just compare this to what we already know about limits and not try to absorb this as its own kind of technical thing. So we know the limit, and the definition of it. If x is close to p but not quite equal to p, then f of x is close to L. That was our definition of limit, and we had deltas and epsilons that went along with it. The limit from the right is going to say the same thing, except x is not only close to p and not quite equal to it, but also on the right side of it and not on the left side. So the formal definition, limit as x approaches p from the right of f of x is L if for any positive epsilon there exists a positive delta, such that for all x in the domain of definition, whose distance from the distance between x and p is less than delta. And here, notice that x is in this pq interval, which means x is to the right of p. So here I'm not asking about all x that satisfy this condition, but only those to the right of p that satisfy this distance to p less than delta condition. Then f of x minus L absolute value is less than epsilon. So the distance from f of x to L is less than epsilon. So here, we're only requiring this conclusion. This conclusion is exactly the same thing that we had for the definition of a limit, but the condition is the only x's which need to satisfy it are those whose distance to p is less than delta, and the x's which are to the right of p. Okay? Here, there's another notation. Instead of this notation, limit x goes to p from the right, f of x equals L, we're at f of p plus. Means the same thing. So p plus, just like p plus here, f of p plus equals L means the limit as x approaches p from the right of f of x is L. That's what this means. So f of p minus, the limit as x approaches p from the left, is defined in a similar way. So here we have to assume that the function is defined at p and at least a little bit to the left of it. Okay? So the function could be defined on both sides of p. All of this makes sense if the function is defined on an even bigger set than this. The minimum assumption is that the function has, for the limit from the right, minimum assumption is the function is defined a little bit to the right of p, but not necessarily to the left, but could be on the left as well. Here I have to assume that the function is defined on the left of p and not necessarily on the right. Okay? So for any positive epsilon, this limit as x approaches p from the left of f of x equals L is L if for any positive epsilon there exists a delta such that for any x to the left of p, and whose distance to p is less than delta, satisfies this condition. Right? So limit from the left, limit from the right, and limit from the left. Okay. So we had a limit, and we then had continuity. So function was continuous at p if the limit at p is the same as the function value at p. We have continuous from the right, continuous from the left. The function is continuous from the right at p. Here I should say at p if the function value at p is the same as the limit from the right. Okay? We see the function is continuous from the left at p if the function value at p is the same as the limit from the left at p. Okay? So just kind of a contextualization, a relationship between this and the previous things that we studied is f is continuous at p if and only if the limit from the left exists and the limit from the right exists, and those limits are equal to each other and to the function value. Okay, so here this is for as long as p is an interior point of the domain of the function. So remember, it doesn't make sense to talk about the limit from the left unless the function is defined, the limit from the right, unless the function is defined to the right of x or to the right of p. It doesn't make sense to talk about the limit from the left unless the function is defined to the left of p. So here this means the function has to be defined on both sides of p, which means p is an interior point. This condition doesn't make sense if p is not an interior point. So we're going to talk a little bit about non-decreasing functions. Same thing, similar things that apply for non-increasing functions. They have very good properties when it comes to limit from the left and right. So the limit from the left doesn't have to exist for a general function. Limit from the right doesn't have to exist for a general function, but for monotone functions, non-increasing, non-decreasing functions, the one-sided limits always exist. Okay? So let's look at a non-decreasing function, right? So the graph is moving up as I move from left to right, and there's a discontinuity here. We say for any p that's not equal to the right endpoint, we're going to talk about the limit from the right. So of course it doesn't make sense to talk about the limit from the right at the right endpoint. So what we're saying here is for any point other than the right endpoint, the limit as x approaches p from the right is equal to the infimum of f of x over this range of x between p and b, including b but not including p. So let's understand geometrically what this is telling me is if I look here at p and I want to know what's the limit from the right, well, first of all, this is saying that limit exists, and it's saying, well, if I look at x's that get closer and closer to p from the right, then the values of these are decreasing, right? So if I look at x's and move them toward p from the right, the x values are getting smaller as I get closer to p from the right. So the x values are getting smaller. If the function is non-decreasing, the outputs are decreasing, or at the very least non-increasing, right? So as x gets closer to p, the outputs are getting smaller and smaller, and then in that case the limit is just the infimum. So take x's over here, look at where they come out over here, and they're decreasing to the y value where this empty hole is. It's the infimum of the values from the right. If I look at values from the right, look at their outputs, they're over here, and the infimum is right here where that empty hole is. Okay. Similar thing happens from the left. As long as p is not equal to the left endpoint, I can talk about the limit from the left. It's the supremum of the f of x for x smaller than p. Right? So kind of the limit from the left is this, where this empty circle is, and it's the supremum of these smaller values that are increasing to that f of p minus. Okay. So a discontinuity like this, where the limit from the left and the limit from the right exist, but they're different, that's a jump discontinuity. Okay. So there are other kinds of discontinuities, but it turns out, so for example, another kind of discontinuity would be where the limit from the right doesn't exist at all. Okay. But for a non-decreasing function, for a non-increasing function, the limit from the left and right exist. They don't necessarily have to be equal. So something nice about monotone functions, functions which are either non-increasing or non-decreasing, the only type of discontinuity they can have is a jump discontinuity. So that's all we have to say for chapter 4. So now we're going to move into differentiability. So we probably remember a lot of this, hopefully remember a lot of this from Calculus 1. So the appropriate context for a derivative is at an interior point, although we can define one-sided derivatives just like we define one-sided limits. That's not going to be something we pay a lot of attention to. When you get into multivariable calculus, it becomes a lot more difficult to talk about limits at boundary points because, well, an interval, you have endpoints. Those are easy to understand. There's only one way to approach an endpoint. If I have some weird region in two-dimensional space, the boundary could also be very weird, and there are lots of ways to approach it, so it's not nearly as common to talk about derivatives at boundary points. So we're usually talking about derivatives at interior points of the domain. So let's assume that we have some function, f, and p is some interior point of the domain. So f is defined at least a little bit to the left and right. Okay. We say f is differentiable at p if this limit exists. Right, so I have f of x minus f of p over x minus p. I take the limit as x goes to p. If that limit exists, then we say that f is differentiable at p. And this limit we can denote it by f prime of p or df dx of p. Okay? The value of this limit is called the derivative of f at p. Okay? And this is our definition of a derivative. So you might remember a different definition, or not a different definition, but a different looking definition. Limit as h goes to 0 of f of p plus h minus f of p over h. You might remember this from Calculus 1. It's equivalent. This isn't a different definition, it just looks different. So here, if I compare this to this, so if I start with this definition, I can say let x equal p plus h, and this becomes this. Okay. If I start with this definition, I can say let h equal x minus p, and then I go from here to here. So if I have one limit, I can get to the other one by doing just a renaming of variables. So these are two different looking ways of defining the exact same thing. And feel free to use either one. Let's try to understand what this is. Okay, so derivatives are rates of change. Okay, so I have a function, and I have some input variable x, and I have an output. Right, so I can look here and here, A, and B, and say, okay, so this might be, well, this doesn't look like a profit function because profit functions are usually monotone, but let's say that this is a profit function, and I say, okay, if I increase the price from A to B, what effect does that have on the profit? And so, so here I can look at delta F, which is the change of the amount of profit over this interval. And I can look at delta X, which is the change in the input. And I can look at the ratio. Delta F, delta X is f of b minus f of a over b minus a. Okay. So I have a triangle here. The base is delta x, the height is delta f. The ratio is the rate of change, which is the slope of the line segment that goes through those 2 points. Okay. And this is a rate. How quickly is f changing with x? Okay. So more or less, if I change the input by this amount, then the output changed by this amount. And this is a location-specific thing. It's not the case that if I change my input by this amount from any starting point to any other point, I'm going to get the same change in the output. This is specifically how much did the output change when I went from A to B. Right? So from A to B, had some difference here. If I pick two other points that have the same difference, I'm not necessarily going to have the same difference in output. So this is location specific, okay? And that's reflected here by the f prime df dx of p. Right? Different p's, I get different values here. Right? I get different rates. So hopefully we all understood this when we went through Calculus 1. But what we like to do is, let's say, fix a point P, and I'd like to know about this instantaneous rate of change, which would be the slope of the tangent line there. And so what I do to approximate the slope of the tangent line is to pick a nearby point, x, and then look at the slope of the line that goes through those 2 points, and we just said on the previous page that that's that. And now, so here's P, which is fixed, and x is not fixed. So we're going to move x around, and the closer x gets to P, the closer the secant line that goes through 2 points is going to be to the tangent line. And so that's the idea, is I fix P but don't fix x. I slide x over to P, and I see what these slopes are doing, and they are approaching, well, assuming the limit exists, they are approaching the slope of the tangent line. So there's our definition of the derivative. Let's get back to the prepared notes. So, like I said previously, if I have a function that's defined as some interval a, b, I could define f prime of a and f prime of b. to be a one-sided derivative, I just take the one-sided limit there. It's the exact same formula here, f of x minus f of a over x minus a, but I take the limit from the right because I can't take the two-sided limit. The function's not defined to the left of a, it's only defined to the right of a, so I have to take a limit from the right. Same thing here, I can define the derivative at b, but the function's not defined to the right of b, so I have to approach it from the left. So I take the limit from the left. So I can do one-sided derivatives, and it makes perfect sense. We don't see it that often, but it's convenient to know that it's there. So differentiability is a notion of smoothness. So here I have a kind of smooth curve here, and I just said at any point I made a tangent line. So kind of the function transitions smoothly as I move from the left to the right. Here's an example of a function and a point P. The derivative does not exist at this P for this function because it's not smooth here. So we typically tend to think of functions which are differentiable as being differentiability is some kind of notion of how smooth the function is. If the function has a sharp cusp like this or a corner, then it's probably not going to be differentiable at the corner or the cusp. So I guess I should say, so we had, if you remember, a notion of continuity at P and then a notion of continuity. Continuity just means continuous at every P. So we define a notion of differentiability at P, and here I'm talking about differentiability. Differentiability just means differentiability at all P. So as we said earlier, the derivative is a rate of change. So often we will write, instead of f of x, we'll just write y. And so we often name our function y instead of f of x. We can write y prime instead of f prime of x. We can write dy dx instead of df dx. And now we will think about this idea. So if we had before, we took the limit. So here we have a limit. And if I cover up the limit and just talk about p and x and think about them both as being fixed, then this makes perfect sense. This ratio makes perfect sense. But now, what are we talking about? What is the usefulness of the limit? Okay? When we take the limit as x goes to p, the result will have p in it. It will be dependent on p, but not dependent on x, and we get the f prime of p. What information is actually conveyed by that f prime of p? Right, so the idea is, if we have f prime of p, or f prime of x here, if we make a small change to the input, then the derivative is going to tell us how much, approximately how much of the output will change. So we have a small change in the input, then if I change the input x by this small amount, the corresponding change in y will be about the derivative times the amount, right? So this is what we know rates do. This is a rate. So I take the amount that I changed to x, multiply it by the derivative, and that gives me approximately the change in y. Okay, so I take an amount times a rate, and I get another amount. This amount is the change in the input, and then the other amount that I get here is approximately the change in the output. Okay? So this is approximate. It's true for small changes in input, where small means different things in different contexts. Okay, so in one problem, small might mean within less than 0.1, and in another problem it might mean less than 0.0001. So small doesn't have some fixed meaning universally. Just it's context specific, it's function specific. But here we have an example. So to think about, let's assume that I have a function, and here at x, the derivative is 2, which means the slope of this line is 2. If I make a small change in the input, the small change in the output is going to be about twice as much, right? If f prime is 2, that means the rate of change in y with respect to change in x is about 2. It means if I change x by some amount, the change in y is going to be about 2 times that, because that's the rate that gets me from x to y. So we're going to get into the kind of the mechanics of it, the actual stuff that we can prove. We're stepping away from the intuition. Let's talk about the rules for derivatives. So we probably remember product rule, quotient rule, chain rule. Hopefully we remember those. We're going to prove those, but not in this lecture. A little bit more technical. Today we're going to do sum rule and constant multiple rule. So we have this rule. This is the sum rule. So when I write this rule, I'm referencing f prime of p and g prime of p. Of course, we know if I just take any old function at any point p, f prime of p doesn't have to exist. The function doesn't have to be differentiable there. Okay? So when I write a formula like this down, what I mean is I'm assuming that f prime of p exists and g prime of p exists, and then the formula is true. Okay? And what it means is if this derivative exists, if f is differentiable at p, and if g is also differentiable at that same point p, then the sum f plus g will be differentiable at that point p. Okay? So we have to understand kind of what are the assumptions here. I'm assuming the derivatives that I'm referencing exist. And then we have this formula. So this formula is intuitive to the point where a lot of students actually don't understand the content of it. So what we're saying here is we have two operations. I can take functions and add them and I get a new function. Okay? But now this f prime of p, that's a number. G prime of p, that's a number. So here, f prime of p plus g prime of p, that's not a function plus a function, it's a number plus a number. Right? So here, on the right side, I'm taking a derivative here of f, I'm taking a derivative here of g, and then I'm adding two numbers. On the left side, I'm adding a function f plus a function g, and then I'm taking the derivative. Okay, so on both sides of the equation, I'm taking a derivative, I'm doing a sum, but the order changes. Here it's sum first and then derivative. Here it's derivatives first and then sum. And the sum rule, which is what this is, you can say sum rule for derivatives because we're going to have a sum rule for integrals as well. Okay. So the sum rule says it doesn't matter what order I do those things in. I can add and then take a derivative, or take a derivative and then add. I get the same thing. It's very nice because if you remember product rule, you know that products don't work that way. Multiply and then take a derivative versus take derivatives and then multiply, you do not get the same thing, usually. Okay. And here's a proof. So if I want to compute this f plus g prime at p, the definition is this. I take the function at x minus the function at p, divide that by x minus p, and take the limit as x goes to p. That is the definition. This is the definition of the derivative of f plus g prime of p. But now we know things about limits, so I can split this, just rearrange this. This is f of x plus g of x. That's the definition of f plus g of x, is f of x plus g of x. This is f of p plus g of p, and I can distribute the minus and rearrange things and split it into two fractions. I'm sorry, this should be x minus p, not p minus x. And now another thing that we know about limits is the limit of a sum is the sum of the limits, assuming they exist, and well, that limit is f prime of p, so the assumption that f prime of p exists is the assumption that that limit exists. Okay? This is g prime of p by definition, right? So this is f prime of p, this is the definition of f prime of p, this is the definition of g prime of p, so those are equal because those are the definitions of these two things. And we did it. We proved that this thing, which is called a difference quotient, for f plus g can be split up into difference quotient for f plus difference quotient for g, and those are the derivatives separately. Okay, so there's a proof of the sum rule. We also have constant multiple rule. If c is a constant, here I'm multiplying the function by c and then taking the derivative. Here I'm taking the derivative of f and then multiplying that by c, and the constant multiple rule says it doesn't matter what order I do those things in, I get the same result. So this is constant multiple rule. So the proof is, well, I start out with this difference quotient. This is the definition of the derivative of c times f at p. So this entire thing is the definition of this derivative. Well, I can use my limit properties again, pull the c out of the limit, and then, well, this is the definition of f prime of p. So these two rules for derivatives follow very easily from corresponding rules for limits.